Kepler-22b keeps getting sold as our second Earth, a perfect blue world waiting 600 light-years away. But the story you've been told about that planet is lying to you. In this video, you're going to see what really happens when you stop dreaming, start doing the math, and ask a brutal question. Not, could we live there? But what would it actually cost to even try? Here's a blunt question. How do you visit a planet that light itself needs 600 years to reach? Not a spaceship, not a rocket. Literal light. The fastest thing in the universe. That's the starting problem with Kepler-22b, and once you really walk through the numbers, it stops feeling like a destination and starts feeling like something outside the human timescale entirely. Kepler-22b is a super-Earth orbiting a star like our Sun called Kepler-22 in the constellation Cygnus. The distance is roughly 600 to 640 light-years. In more familiar terms, that's around 6 quadrillion kilometers, or about 4 quadrillion miles. A light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second, roughly 186,000 miles per second. Even at that ultimate speed, the one-way trip takes you about 6 centuries. Leave today, arrive in a future where your language has changed, your culture has changed, and your entire civilization is basically history. Now here's the part that really hurts you. You do not get any discount for trying hard. Every percent of light speed you fail to reach blows up the travel time. You miss light speed by just 1%, so you go at 99% instead of 100, and the trip stretches beyond 600 years. Drop to 10% of light speed, and now you're talking about thousands of years. Slip all the way down to 1% of light speed, and you are in the tens of thousands of years range. The distance is fixed. Your speed is what decides whether this is barely possible or completely outside human history. So what can you actually do right now with real hardware? The fastest object humans have ever built is NASA's Parker Solar Probe. At its peak, when it swings very close to the Sun, it reaches about 190 kilometers per second. That's roughly 690,000 kilometers per hour, around 430,000 miles per hour. That sounds absurdly fast. In everyday terms, that's like circling Earth in a few minutes, but compared to light, it is tiny. That record speed is only about 0.064% of light speed. If you take that real measured speed and drag it across 600 light-years, you do not get a heroic multi-generation journey. You get something like 1,000,000 years of travel time. 1,000,000 years ago, your species did not exist in its current form. That is the level of timeline you are playing with. You are not planning a mission, you are laying down a path that runs across evolutionary time, and that is just to get from here to there. So you might say, fine, let's go beyond anything we have, let's talk 1% of light speed. 1% of light speed is about 3,000 kilometers per second, which is roughly 6.7 million miles per hour. That is almost 16 times faster than Parker Solar Probe's peak speed. At that speed, you have stepped far outside normal rocketry into a regime where everything is pushed to the edge. And still, even if you somehow reach 1% of light speed, the trip to Kepler-22b takes on the order of 60,000 years. That is longer than all of recorded history by a big factor. Push harder, go to 10% of light speed. 10% light speed is about 30,000 kilometers per second, around 67 million miles per hour. Now you are firmly in what physicists call relativistic speeds, where the effects from Einstein's special relativity become important. This is the kind of speed you see in serious science fiction. But when you divide the distance to Kepler-22b by that speed, you still get a number of about 6,000 years for a one-way trip. 6,000 years ago, humans were building the first big cities and early writing systems. You're asking a single mission to remain stable for at least that long. So people often bring up a different idea, the generation ship. The argument goes like this. The original crew never arrives, and many generations later, their distant descendants are the ones who actually reach Kepler-22b. On the surface, that sounds like a clever workaround. You avoid the problem of a human lifetime by treating the ship as a long-running community instead of a long flight. But now look at what you're actually demanding. You need a closed ecosystem that stays balanced, not for decades or centuries, but for tens of thousands of years. You need water, air, soil, microbes, plants, animals, all cycling perfectly, without any major breakdown, over a time period longer than any human institution has ever survived. No country has lasted that long, no empire, no company, no system. Languages mutate beyond recognition over just a couple thousand years. Cultures shift completely. On a generation ship, you need not just biology to stay stable, but social systems, education, engineering practices, and knowledge transfer, all holding together across hundreds of generations with no backup from Earth. Even if you are extremely optimistic about human cooperation and technology, the odds of that structure staying coherent, never collapsing, never losing critical knowledge, never tearing itself apart socially over a timescale of 6,000 to 60,000 years are very low. The distance to Kepler-22b is not just far in kilometers, it is far in how long can humans keep anything working without a reset. And over everything, there is a final hard limit that you cannot negotiate with, the cosmic speed limit. Special relativity says that nothing with mass can reach the speed of light. As your ship goes faster, closer to light speed, its energy requirement grows in a nasty way. At low speeds, doubling your speed might mean roughly 4 times as much energy. As you approach light speed, each small increase in speed needs more and more energy than the last one, until the required energy heads toward infinity. In simple terms, the universe lets light move at its maximum speed, but anything that has mass, like your starship, gets punished harder and harder the closer it gets. That means there is no hidden trick where you just push a bit more and cut your travel time from thousands of years down to a single lifetime. You cannot simply say we will go at 99.9% of light speed and call it done, because reaching that kind of speed with a ship big enough to carry humans and life support would require ridiculous amounts of energy, way beyond our current global output, possibly beyond what a full planetary civilization could provide without devoting almost everything to that single task. So before you even start worrying about landing on Kepler-22b, breathing its air, or walking on its surface, you hit these 4 connected problems: distance, speed, time, and energy. When you plug in realistic or even very optimistic numbers, they do not give you a heroic challenge. They give you timelines that crush human lifespans and energy demands that crush human industry. And that leads to a more unsettling question. Even if you could throw that much energy and effort at the trip, is Kepler-22b actually a good place for humans to land in the first place? Or is the planet itself another kind of dead end? Here's a hard question. Why are you calling Kepler-22b another Earth, when almost everything we know about it says it's a different kind of world? You beat the distance problem in your thought experiment, you cross those hundreds of light years, you arrive in the Kepler-22 system, and the planet waiting for you is not a familiar blue marble. It is heavier, thicker, and far less friendly to a human body. Start with the picture that made people excited. Kepler-22b orbits in what we call the habitable zone of its star. That is the distance range where, in theory, liquid water can exist on a planet's surface if the atmosphere is right. Kepler-22b goes around its star at about 0.81 astronomical units, a bit closer than the Earth is to the Sun, and its year is roughly 290 Earth days. On paper, that sounds fine. You have a Sun-like star, a comfortable orbital period, and a calculated equilibrium temperature that could sit in the same ballpark as Earth's average. So the first story was simple. This might be an Earth twin at long distance. A planet, in the right zone, around the right kind of star, maybe with the right temperature. But habitable zone is a very rough label. It says nothing about surface pressure, nothing about the thickness of the atmosphere, nothing about the chemistry of that atmosphere, and nothing about whether there is any solid ground you can stand on. You can have a planet in the habitable zone that is an ocean world, a steam world, or a mini Neptune with deep, crushing layers of gas. That brings you to the second, more serious problem: size. Kepler-22b is not the same size as Earth. Its radius is roughly 2 to 2.4 times Earth's radius. In exoplanet language, that makes it a super-Earth. Bigger than Earth, smaller than Neptune. That label sounds like an upgrade, but for a human body it is a warning sign. If the planet has a density similar to rock and metal like Earth, then simple scaling tells you the surface gravity could be somewhere around 2 to 3 times Earth's gravity. At 2g, your weight is doubled. If you weigh 70 kilograms on Earth, you feel like 140 kilograms on Kepler-22b. At 3g, just getting out of a chair becomes hard work. Your heart has to push blood against a much stronger pull, your joints and bones take constant extra stress, and moving around for long periods could be dangerous. You can train for high G the way fighter pilots do, but that works for short bursts, not for everyday life. Human bodies evolve for about 1g. Long-term life at 2 or 3g is not just uncomfortable, it may be impossible without major biological or technological help. So already before you know anything about oceans or continents, Kepler-22b is telling you, I am not built for your skeleton. Now look at mass and the composition, because this is where the picture shifts from heavy Earth into maybe something else entirely. Observations do not give an exact mass yet, but they do put limits. The data suggest a mass somewhere in the single to few dozen Earth mass range. NASA's catalogue lists a best estimate of around 9 Earth masses. Combine that mass with a radius around 2 to 2.4 times Earth's, and you get an average density lower than Earth's. Lower density with higher mass is a clue. It hints that Kepler-22b may not be a simple scaled-up rock, but something with a lot more light material, so-called volatiles. That could mean a massive water layer, deep global oceans, or a thick envelope of hydrogen and helium. Instead of continents and shallow seas, you might be looking at a water world or a mini Neptune. The surface, if there even is a clear surface, might be buried far below thick clouds and many kilometers of supercritical fluid at pressures and temperatures that would destroy normal spacecraft. If the planet tends toward mini Neptune rather than mega Earth, what does landing even mean? You're not sending a probe to a rocky beach. You may be dropping through a deep atmosphere where pressure and temperature rise fast, until metals soften and electronics fail. The world might have no solid ground you can reach at all, just deeper and deeper layers of hot compressed fluid. This is why habitability and reachability are two very different things. Even if some models suggest that Kepler-22b could, under the right atmospheric setup, have an ocean surface at around 22 degrees Celsius, about 72 degrees Fahrenheit, that is only telling you about a possible temperature at some level in the atmosphere. It does not tell you if that level is at a reasonable pressure. It does not tell you if the air there is poisonous, and it does not tell you if you can actually operate there without being crushed. You might calculate a nice Earth-like equilibrium temperature, but the real environment at the level where a human would try to live could still be extreme. You cannot declare a world safe for humans just because some altitude in the atmosphere has a pleasant number on a chart. So when people say, Kepler-22b might be 22 degrees, maybe it has liquid water, let's go, they are skipping the hardest questions. What is the surface pressure? Is the atmosphere thin like Earth's, or thick like Venus? Is it mostly nitrogen and oxygen, or mostly carbon dioxide, hydrogen, or methane? Are there clouds of corrosive chemicals? Is there a strong greenhouse effect that pushes the surface into oven conditions? Or is the planet so massive and so gassy that you never reach a solid surface at all, you just dive into deeper, darker layers until your ship fails? This is where the original dream of another Earth collides with the hard numbers. You're not sending a tiny probe to fly by and take some photos. You're talking about sending human crews to a world more than twice Earth's radius, probably with a thick and complex atmosphere, and maybe with gravity in the 2 to 3g range. You're spending unbelievable energy crossing 600 light-years over thousands of years just to arrive at a place that might be literally unwalkable. And that raises the next problem. If the planet itself is already this extreme, what happens when you look at the engines and the fuel you would need to even try to get there, and realize that our basic way of moving rockets through space breaks down completely at the speeds you would need? Here's the nasty twist. the faster you try to go, the worse rockets actually work for you. Not emotionally, not psychologically, just mathematically. Long before you worry about building a city in space, the basic physics of rockets tells you cannot just keep adding fuel and expect to turn Kepler-22b into a reachable target. The core problem has a name, the rocket equation. Every time you add more propellant to push your ship to a higher speed, you also make the ship heavier, so you need even more propellants to push all that extra mass. Your possible change in speed grows only slowly as you pile on fuel, while your total mass grows brutally fast. You do not get a straight line, you get a curve that flattens out hard. Double the speed you want, and the amount of fuel you need can explode by factors of 10, 100 or more. Rockets are great for going from ground to orbit or from orbit to the moon. They are terrible at we want to go 1,000 times faster than we do now. So how far can normal rockets push you inside this trap? Chemical rockets, the kind we actually fly, throw exhaust out the back at a few kilometers per second. The famous Saturn V of the moon rocket had an upper stage with an effective exhaust speed of around 4 kilometers per second. Modern high-performance chemical engines, using liquid hydrogen and oxygen, sit in the same general range. That sounds impressive, and it is, for climbing out of Earth's gravity well. But compare that to 1% of light speed, which is about 3,000 kilometers per second. Your exhaust is moving at walking pace compared to the speed you actually want. Here is the painful consequence of that. If your exhaust goes out the back at only a few kilometers per second, and you're trying to push the ship up to thousands of kilometers per second, the rocket equation demands an insane mass ratio. You end up in a situation where almost all of your launch mass is fuel, tanks, and structure to hold that fuel, and the actual payload, the part of the ship that carries people, life support, and useful hardware, is a tiny fraction on top. It is like trying to move a grain of sand by building a mountain of explosives underneath it. On paper, with ideal materials and no structural limits, you can write down a number. In real engineering, that mountain of fuel collapses under its own weight. Or you bankrupt your entire civilization trying to build it. So maybe you say, fine, chemical fuel is old tech, let's use something hotter. Nuclear thermal rockets replace chemical burning with a reactor that heats hydrogen directly. That can give you exhaust speeds of maybe 8 to 9 kilometers per second. Better, but still nowhere close to the thousands of kilometers per second you want for interstellar travel. Advanced ion thrusters push exhaust even faster, into the tens of kilometers per second, and they are incredibly efficient in terms of how much thrust you get per kilogram of propellant. But they push very gently. They are like extremely efficient, extremely weak engines. You can leave them running for months or years to slowly build up speed, and that is great for moving unmanned probes around the solar system. The problem is, even if you run an ion drive for years, and you're very patient, you're still nowhere near 10% of light speed. You also have to remember what that years of acceleration means in deep space. Your ship is sitting out there the whole time, exposed to cosmic rays, micrometeoroids, and every other hazard, while the engines gently nudge it forward. You're stretching a fragile machine and a fragile crew across decades, and at the end of all that, you still fall orders of magnitude short of the speeds needed to bring 600 light-years down into anything like a human window. So if the engines struggle this badly, how ugly do the energy numbers actually get when you push them to interstellar speeds? Take a ship with a mass of 1,000 tons. That is not a giant sci-fi city. That is just a modest, dense starship plus shielding, plus life support, plus structure. 1,000 tons is like a small city block or a big ocean ship stripped down and rebuilt for space. Now you ask, how much energy do you need just to accelerate that mass to 10% of light speed? The answer is an insane amount. The kinetic energy at that speed is on the order of 10,000 times the current total annual energy use of the entire human civilization. Not 10 times more, not 100 times more, but 4 digits above everything we do right now, all power plants on Earth combined, for a full year. And that is just to speed up. If you plan to arrive at Kepler-22b and not shoot straight through the system and keep going into the dark, you have to slow down again. That means you need roughly the same amount of energy on the other end, which doubles the bill. At this point, you can ask a blunt question: where does that kind of energy come from? A single country cannot pay for this. You're not talking about one space agency, you're talking about a big fraction of the entire planet's industry and power generation, tied up for a long time to feed one mission. Either you build massive power collectors in space, maybe harvesting a huge chunk of the sun's output, or you accept that you are diverting serious power away from everything else humanity wants to do, like running cities, handling climate, and keeping billions of people alive. This is where the whole plan stops looking like build a bigger rocket and starts looking like rebuild civilization around this one goal. The fuel and energy requirements are not just hard, they are civilization scale. You're turning continents' worth of industry and decades or centuries of global power production into raw speed for a single ship that will vanish into the dark and, if everything goes right, send a signal back in many thousands of years. So the real question becomes, even if you could engineer that energy monster, should you? Is it smart for any civilization to pour that much power and material into one fragile vehicle, moving through a hostile medium when space itself is trying to tear it apart atom by atom for the entire length of the journey? Here's the next move people try. If normal rockets are hopeless, why not jump to the cool stuff: light sails, fusion antimatter, all the advanced drives you see in serious space forums and sci-fi. If you can push a ship to 10 or 20% of light speed, surely Kepler-22b comes back into play, right? This sounds good until you look at what these systems can actually push and what the trip still looks like even if they work perfectly. Start with laser sails. The basic idea is simple. Instead of carrying fuel, you carry a huge, thin, reflective sail, and a massive array of lasers back near Earth pushes on that sail with light. One of the best-known concepts, Breakthrough Starshot, wants to do this with probes that weigh just a few grams. The plan is to hit those sails with many gigawatts of laser power and push the probes up to about 20% of light speed. At that speed, you could send a chip-sized camera to a nearby star in a few decades. For tiny robotic probes, this is an amazing idea, but notice what makes that work. The payload is basically a postage stamp of electronics. The sail is extremely thin, lighter than any foil you use at home. The acceleration is brutal, thousands of times Earth gravity, which a chip can survive but a human cannot. And even with all that, you still need tens to hundreds of gigawatts of laser power on the ground, focused through the atmosphere, coordinated perfectly just to move a few grams. Now scale the hat up honestly. You're not trying to push a gram-scale chip. You want a rotating habitat with farms, radiation shielding and space for thousands of people. Easily tens of thousands to hundreds of thousands of tons. That is a factor of billions heavier than a Starshot probe. If it takes tens or hundreds of gigawatts to push a few grams, pushing a ship that is a billion times more massive would need laser power that makes our entire current global electricity production look tiny. You're talking about power output far beyond what every power plant on Earth produces combined, and you would need to sustain it for long periods. And that is before you deal with the optics problem. Lasers do not stay perfectly tight beams forever. They spread. Over many millions or billions of kilometers, keeping that beam precisely aimed on a sail is extremely hard. Over light years, it becomes nearly impossible with any realistic mirror or lens. If the beam spreads, the light intensity on the sail drops, your acceleration falls, and the whole plan fails. You also have to build a sail material that can survive intense laser light without melting or tearing, and that can stay intact for as long as you need to push. So laser sails are fantastic for small probes, and almost useless for giant human ships. So you jump to the next big thing in the wish list: fusion drives. Fusion is what powers the sun. In a reactor or engine, you would force light nuclei like hydrogen isotopes to fuse together, releasing huge amounts of energy and very fast-moving particles. A fusion rocket could in theory throw exhaust out the back at thousands of kilometers per second, instead of just a few like a chemical rocket. Project Daedalus, a famous study from the 1970s, suggested that a fusion-powered probe might reach around 10% of light speed on paper. This sounds like a solution, until you ask a simple question. Where is our working fusion power plant on Earth right now? We do not have one. We have experimental reactors that can briefly get close to breaking even, but nothing that runs steadily and produces net power for years, let alone decades. Turning fusion into a compact, controllable rocket engine is even harder. You need a system that can handle extreme temperatures, massive neutron radiation, and constant mechanical stress, and that has to operate basically perfectly for many decades of continuous firing. There is no engineering path from where we are today to a fusion starship in the near future. It is still theory, design studies, and lab experiments. Then there is antimatter, the ultimate on-paper fuel. When matter and antimatter meet, they annihilate and convert almost all their mass into energy. Per kilogram of fuel, the energy available is staggeringly high, far beyond chemical or even normal nuclear reactions. If you just look at the numbers, antimatter engines seem perfect for starships. Reality hits very fast. Right now, our particle accelerators can make only tiny amounts of antimatter, nanograms per year, at enormous cost. To fuel a starship, you would need many orders of magnitude more, and you would need to do it reliably and safely. Then you need to store it. You cannot put antimatter in a tank, it annihilates the walls. You have to suspend it in magnetic fields in near-perfect vacuum at very low temperatures for centuries or millennia, while cosmic rays and electrical faults constantly try to knock it out of its trap. A leak is not a spill, it is an explosion. Designing a system that holds even grams of antimatter without failure over the full length of an interstellar trip is not just hard, it is an extreme safety nightmare. So after running through laser sails, fusion, and antimatter, where do you really end up? You do not get a quick hop to Kepler-22b. Even if you grant yourself a miracle engine that can push a big human ship to 10 or 20% of light speed, the basic geometry of the situation does not change. At 10% light speed, crossing 600 light years still takes around 6,000 years in the ship's own frame of reference. At 20%, you are still dealing with a journey of a few thousand years. Relativistic time dilation, the effect where time slows down for fast-moving objects, does not help much at these speeds. At 10% of light speed, the difference between time on the ship and time back on Earth is tiny, less than 1%. Even at 20%, the factor is still close to 1. You need to go to 99% of light speed and beyond before time dilation really bends the timeline in your favour. And those speeds push the energy demand so high that they move from advanced engineering into practically impossible. So the bottom line is clear. Exotic drives change the numbers on the page, but not the category of the problem. They can maybe turn 60,000 years of travel into 10,000 or 6,000. They do not turn Kepler-22b into a destination you can reach with one crew in one human lifetime. Advanced propulsion does not give you, let's go there and come back with photos and rocks. It gives you, maybe if everything holds together for many generations, somebody related to you very far down the line eventually arrives. And that leaves one more brutal question. Even if you solve the propulsion puzzle, build the miracle engine, and launch your giant ship to these extreme speeds, what does interstellar space itself do to you? When every atom of gas and every grain of dust in your path starts hitting you with the energy of a weapon? How do you keep a ship alive when almost empty space starts acting like a sandblaster running at a significant fraction of light speed? You solve the rocket problem in your head, you solve the fuel problem with miracle engines, you decide to cruise at 10% of light speed toward Kepler-22b, and suddenly the space between the stars stops being background and turns into a constant physical threat. Between stars, the interstellar medium sounds harmless. On average, you get just a few atoms in every cubic centimetre. So compared to air at sea level, which has trillions and trillions of particles in the same volume, it looks practically empty. But emptiness is not what matters here. Speed is. Around 0.1 light speed, which is roughly 30,000 kilometers per second, about 67 million miles per hour, Every single one of those atoms hits your ship with huge energy. Each impact is like a tiny high-speed bullet. And then there is dust, little grains of rock or ice, maybe millimeters across, scattered all through space. At those speeds, each one is not dust anymore. It is a tiny missile. Think about a 1 milligram grain. That is a speck you can barely see on your fingertip. At 10% of light speed, that tiny mass carries roughly the energy of a hand grenade when it slams into your hull. Now multiply that by the number of grains you will meet over trillions of kilometers. You're not talking about one impact in the whole trip. You're talking about a continuous hail of micro-explosions on your forward surfaces, non-stop for thousands of years. And if you ever think about going faster, to half of light speed or 9/10, the energy per grain jumps into completely destructive territory. At that point, a single unlucky hit from a slightly larger chunk could rip a hole straight through your ship. So your hull is not just a shell to hold in air, it becomes a sacrificial layer. You expect it to be eaten away slowly by all these impacts. It has to be meters thick in the direction of travel, made of metal, water, ice, or some layered combination, so that incoming particles chew through the outer layers instead of hitting the living space behind. This is called shielding, but in practice it is more like a giant, slowly dying bumper that you accept will be destroyed over the course of the journey. To make that work, engineers talk about Whipple shields, which are multiple thin layers spaced apart, designed so that an incoming particle shatters on the first layer and spreads out its energy before it hits the next layer. You might also add magnetic deflectors, powerful fields that push away charged particles, and maybe a forward debris barge, a big dense object flying ahead of the main ship, taking the worst hits first. But here is the catch. Every centimetre of extra material you add to the front of the ship means more mass. Scale this up to a city-sized arc, and every centimetre of aluminum, water or ice on that nose section can add thousands of tons. All that mass feeds directly back into your propulsion problem. You need more energy to push it, more engine, more fuel, more everything. There is a real-life warning sitting in our own solar system, Parker Solar Probe. It only goes about 190 kilometers per second, roughly 700,000 kilometers per hour, 430,000 miles per hour, much slower than 10% of light speed, but still the fastest spacecraft we have ever flown. To survive near the sun at that speed, it needs a sophisticated carbon composite heat shield, careful planning of its path, and constant monitoring. And that is inside the sun's influence over a short mission in a region where we roughly understand the particle environment. Now compare that to what you're proposing more than 15 times faster outside the protective bubble of the sun, in a harsher and less predictable region for tens of thousands of years. It is like the difference between riding a bike for an afternoon and driving a race car flat out on a track you have never seen for your entire life without a pit stop. The shield Parker uses is already close to the edge of what we can engineer. A true interstellar arc would need something much more extreme, and it would need to keep working far longer. There is another problem you cannot engineer away with confidence. You do not have a complete map of the shooting range you are flying through. We do not possess a three-dimensional chart of every dust clump, every dense patch of gas, every rogue pebble on the path from here to Kepler-22. We can map large structures, clouds and general densities, but not individual threats. At relativistic speeds, there is no such thing as dodging at the last second. By the time your sensors pick up an object in front of you, you're already right on top of it. The time between detection and impact can be shorter than the time it takes to even process the data, let alone move a city-sized ship. So you end up betting the entire mission on probability, hoping that the average density along your path stays low, that there are no high-density patches, no unexpected debris fields, no hidden larger rocks. A single unanticipated dense region, a cluster of bigger grains, could peel away the front of your interstellar arc like thin metal, expose the inner habitat, and kill the mission in seconds. All of this is happening while your engines burn through staggering amounts of energy just to keep you on course and up to speed. And even if you somehow build that sacrificial shield, add the magnets, fly a debris barge in front, thread the path correctly and survive the endless impacts, you still have not dealt with one more, slower, invisible threat. Over thousands of years in deep space, the constant rain of high-energy particles, cosmic rays and radiation is quietly going through the hull, into the ship and into your crew. You can armor against dust, but how do you protect human bodies and their DNA from being marinated in cosmic radiation for millennia? How long do you think a human body can sit in deep space before radiation quietly ruins it from the inside out? 10 years, 100, 1,000? Once you leave the sun's protective bubble and head toward Kepler-22b, you are not just in the dark, you are sitting in a slow, constant radiation bath that never stops, and it keeps hitting you for as long as the ship exists. Outside the heliosphere, you're exposed to galactic cosmic rays. These are not gentle sunlight or normal X-rays from a hospital. They are high-energy protons and heavy atomic nuclei moving at relativistic speeds, launched by supernovae and other violent events all over the galaxy. On the International Space Station, which is still inside Earth's magnetic field part of the time, astronauts already get roughly 0.3 to 1 millisievert of radiation per day. A long Mars mission, a few years round trip, would push astronauts close to or beyond what we currently consider a safe lifetime dose. An interstellar mission to Kepler-22b is not a few years, it is thousands of years, so you're talking about orders of magnitude more exposure. The first instinct is simple: add more shielding, make the walls thicker. But radiation does not behave like bullets in a movie. If you build walls out of heavy metals like lead, high-energy cosmic rays slam into those atoms and create showers of secondary particles which can spread the damage inside. In some cases, a thick metal hull can make things worse by turning one incoming particle into a cascade. Materials like water, plastics, and other hydrogen-rich compounds are better. They slow and absorb the particles more gently, but to cut the radiation down to comfortable levels, you are not talking about a few centimeters, you are talking about meters of material around the living areas. For a realistic rotating habitat big enough for thousands of people, that means you are basically building your city inside a hollowed-out asteroid, or inside an artificial shell as massive as a small moon. That solves some of the radiation exposure, yes, but it turns your ship into a full-scale mini-world, which again explodes the mass, and therefore the energy you need to move it. The more you protect your crew from radiation, the heavier the ship gets, and the harder it is to accelerate it to even 10% of light speed. Meanwhile, the people inside are still biological organisms running on DNA. Human cells can repair some radiation damage, but not all. Chronic exposure leads to higher cancer rates, higher chance of cataracts, problems in the nervous system, and damage to cells. We know how bad this can get over a few decades from studying nuclear workers and accident survivors on Earth. Now stretch that environment across thousands of years, hundreds of generations, under a constant but variable cosmic ray background. You're not maintaining a normal human population, you're applying continuous pressure that slowly filters who can survive and who cannot. In that scenario, the population on the ship starts to change. Maybe you add gene editing to try to control it. Maybe only those with naturally stronger repair mechanisms, or with certain engineered traits, live long enough to have many children. Over time, the baseline for normal on the ship drifts away from what you call human today. The environment selects for radiation resistance, not for your current health standards or appearance. You said you wanted to send Homo sapiens to Kepler-22b, but the ship is pushing you towards something else, step by step, generation by generation. On Earth, you forget how much protection you really get for free. Above every square meter of ground, there are around 10 tons of air stacked up, acting as a shield. Earth's magnetic field guides many charged particles away or into the poles, where they harmlessly light up as auroras instead of slamming into your DNA. In deep interstellar space, you lose both. There is no thick atmosphere. There is no stable planetary magnetosphere. You can try to build artificial magnetospheres with giant coils and plasma bubbles, but these are speculative, energy-hungry, and they mostly help against charged particles. They do almost nothing against neutral particles or high-energy photons like gamma rays, so you are stuck with a mix of massive physical shielding, active magnetic systems, and medical interventions, all of which have to keep working for as long as the ship lives. There is no safe outside to escape to, no hospital that is not also inside the same radiation field. Every failure is cumulative. Every small increase in leak rate, every slowly degrading magnet coil means more damage over time. Think about what that does to identity. After thousands of years, constant radiation pressure, and likely deliberate bioengineering to avoid collapse, the crew that finally reaches the Kepler-22 system will not be like you. Their genome will have drifted, both randomly and by design. Their bodies may be better at repairing DNA, better at handling low-level damage, may be different in ways you would find uncomfortable or strange. Their culture will have grown around the ship environment, not around a planet. For them, the idea of normal Earth human will be a legend, not a reality. So when people talk about humans landing on Kepler-22b after a realistic interstellar cruise, that word hides a lot. What arrives is not a simple extension of the people who launched. It is closer to a new branch of the species, or even a new species, adapted to extreme radiation, closed habitats, and endless night. The landing is less like explorers stepping onto a new world, and more like the end of a very long space station event that just happened to take place inside a metal and rock shell, instead of on a continent. And that sets up an even harder problem. If your crew is slowly changing just to survive the trip, what about everything else they need to bring with them? The plants, animals, microbes, air, water, and machines that have to stay in balance, not for years or centuries, but for tens of thousands of years, with no reset button, no resupply, and no backup planet. How do you keep people alive in a closed box for 10,000 years when the best test we have on Earth barely stayed stable for 2? Before you think about walking onto Kepler-22b, you have to face the fact that your ship is not just a vehicle, it is a full biosphere. And biospheres are messy, chaotic systems that fight back when you try to seal them. We already tried a small version of this. Biosphere 2 in Arizona was built as a closed ecological system with soil, plants, animals, and humans sealed under glass. The goal was to see if a miniature Earth could run itself. In practice, it struggled badly. Carbon dioxide levels swung up and down, oxygen dropped, some species exploded in number while others died out, and weird chemical reactions in the concrete sucked away gases in ways the designers did not expect. And that was over about 2 years, with Earth right outside ready to help. Now scale that to a starship. You're not asking for a stable system for 2 years, you're asking for tens of thousands of years, with no resupply from Earth, no fresh soil, no spare microbes, no new seeds from the outside. Every plant, every fungus, every insect, every bacterium has to find a long-term balance and stay in it, as generations of humans eat, breathe, farm, and change their own environment. A small drift in the wrong direction over a few centuries can turn into a total collapse. The core issue is mass balance. On Earth, you do not think about where every kilogram of nitrogen or phosphorus or trace metal goes, because the planet is huge. Plate tectonics moves rocks around, rivers bring nutrients back to the sea, volcanoes and weather return elements to the air and soil, and life cycles them endlessly. On a ship, you do not have that. You have a glorified terrarium, a fixed amount of material, maybe a few million tons at most, and it all has to cycle perfectly. Every kilogram of nitrogen has to come back as usable nitrogen. Every bit of phosphorus locked into bone or waste has to be recovered, processed, and put back into soil or hydroponic tanks. If even a few % of something essential slowly leaks into an inaccessible form, into the hull, into deep plumbing, into a trapped chemical compound, your ecosystem starts to run short. On Earth, that shortfall gets diluted across oceans and continents. On a ship, it can mean your crops fail, your oxygen production drops, or key microbes die off. The system does not care that you are on a mission, it just runs its chemistry. So maybe you decide to lean more on machines. You can replace some of the biological loops with technology, with closed-loop carbon dioxide scrubbers, water recyclers, hydroponic farms, and synthetic food production. We already fly small versions of these on the International Space Station, recycling water from humidity and waste, cleaning air. But look at the timescale. Today's life support hardware is designed for years, maybe a couple of decades at best, with constant maintenance and resupply. Electronics degrade, lubricants break down, seals crack, filters clog, pumps wear out. On a 6-month trip to Mars, that is a serious engineering job. On a 10,000-year cruise to Kepler-22b, it is a fantasy, unless you completely change the way you build and repair machines. To make that work, you would need self-repairing infrastructure, systems that can diagnose their own damage, manufacture their own replacement parts, and integrate new components over and over longer than all of recorded history. That does not just mean a clever air filter. It means full recycling factories, 3D printing on industrial scales, mining and a refining of scrap metal and plastic from old systems, and a continuous upgrade path that never gets stuck. You are not just fielding a spacecraft, you are fielding an entire industrial base in a sealed shell. Then comes the human side, maintenance across generations. Even if you design beautifully redundant systems, triple backups for everything, they only stay alive if people know how to fix them. You need an unbroken chain of trained engineers, technicians, and scientists passing down knowledge, blueprints, and skills, not for 50 years, but for hundreds and thousands of years. That means libraries that survive language drift, education systems that do not collapse, and a culture that keeps valuing the hard, boring work of maintenance, century after century. At that point, what you have is not really a ship anymore. It is a fully industrialized micro-civilization. It needs farms, factories, power plants, recycling hubs, labs, schools, and governance structures that prevent it from falling into a dark age. If one generation rebels and decides that the old manuals are ancient nonsense, or if a war, plague, or internal collapse wipes out the technical class, your life support does not care. It keeps running until something breaks, and then people start dying. Underneath all of this is a one-word enemy: entropy. Everything breaks down over time. Bolts corrode even in controlled atmospheres. Plastics slowly outgas chemicals and become brittle. Insulation cracks. Radiation from both space and your own power systems slowly damages materials, makes metals harder and more fragile, weakens seals and cables. On Earth, when infrastructure gets too old, you abandon it, bulldoze it, build a new bridge, a new plant, a new city block. On an interstellar ship, you have only what you launched with, plus what you can recycle from your own old systems. There is no fresh steel from an outside mine, no new batch of copper pulled from a distant mountain. Stretch that across a timeline of 6,000 to 60,000 years. Even if each individual system has a small chance of failing in any given decade, that probability compounds. Over enough time, the chance that you suffer at least one catastrophic unfixable failure creeps toward 1. Maybe it is a slow leak in a crucial tank, maybe a silent fault in a reactor, maybe a corrupted archive that erases key manufacturing recipes. Whatever it is, there is no outside help. The system stands or falls entirely on its own. So when you talk about going to Kepler-22b, what you're really talking about is running a complete planetary-level life support experiment in a metal can, with no pause button, for a period of time that dwarfs anything humans have ever managed to keep stable. And that leads directly to the next hard question. Even if you somehow keep the hardware and biology alive, can human cultures, laws, and goals stay aligned with a mission that lasts longer than any civilization we know? Or does the project itself tear apart under its own timescale? How do you keep a mission on track when the mission lasts longer than any civilization we have ever built? The problem is not only distance or engines, it is time, raw calendar time, and human cultures are simply not designed to hold the same goal steady across thousands of years. Look at the longest running things we know, a handful of cities, a few cultural traditions, stretch back maybe 3,000 to 4,000 years. That is impressive, but even that upper limit is still shorter than an optimistic 6,000-year trip to Kepler-22b at 10% of light speed. Most countries, empires, corporations, alliances last a few hundred years at best, then they split, merge, or vanish. Languages drift so far that people separated by a millennium often cannot understand each other without study. You're talking about a mission that runs for longer than the gap between ancient Mesopotamia and you expect the purpose to stay crisp, unchanged, and binding. Then comes the question of who is in charge. Earth launches the ship in, say, the 21st or 22nd century. There is some founding charter, some mission statement, some constitution written in the language of that era. Fast forward 1,000 years on board. For those people, that original document is old history. It will feel as distant to them as Bronze Age law codes feel to you. In that time, they will have had arguments over power, maybe revolutions, maybe reforms. That is not a failure, that is how human societies evolve. Information is not stable either. Digital storage does not last forever. Bits flip, drives fail, formats become unreadable. You can copy and recopy archives, but that assumes each generation understands what it is preserving and cares enough to maintain it. Meanwhile, language keeps changing. Words shift meaning, grammar evolves, new slang appears, old concepts fade. The careful explanations recorded at launch might read as confusing or even meaningless a few hundred years later. Over enough time, the mission's original purpose is at risk of turning into legend. People might start telling simplified stories, "Our ancestors fled Earth," or "We are chosen to reach the promised world," depending on how culture evolves. New ideologies can attach themselves to the idea of Kepler-22b or strip it away entirely. It is completely realistic that after a few centuries of life confined to the ship, a large fraction of the population simply decides they do not want to commit to arrival on some distant planet that no one has seen. They might prefer to stay in space, modify course to another target, or even slow down and live as a permanent space habitat civilization. From Earth's side, there is nothing you can do about that. You cannot send new orders and expect them to be followed in real time. At a distance of hundreds of light years, every message takes centuries to arrive. You send a policy update. Your great-great-great-great-grandchildren see the reply. Once the ship is a few light years out, it is effectively a separate civilization. It has its own problems, its own crises, its own alliances and conflicts. It handles them locally. You might still exchange data, but you're not running a mission control. You're talking to a foreign society with its own agenda. That also means you cannot recall the mission. If Earth discovers a better target or a major danger in the Kepler-22 system, it can send a warning, but that warning crawls at light speed. By the time it arrives, the ship's situation may have changed completely. Its engines may be off. Its culture may have diverged so far that the message is just an odd historical note. You're not steering a ship, you're launching a new branch of civilization and hoping it chooses to keep going in the direction you marked out at the start. Meanwhile, the target is not standing still. Stars orbit the center of the Milky Way, bobbing up and down through the galactic disk, drifting relative to each other. The Sun moves, Kepler-22 moves, nearby stars move. Over millions of years, the pattern of the constellations completely changes. Over tens of thousands of years, there is still noticeable drift. Your navigation has to account not just for your own motion, but for the changing position of the destination and the changing gravitational landscape along the way. You will navigate by background galaxies, by pulsars, by distant quasars, by carefully modelled stellar positions. But all of that depends on reference frames and catalogues that must be updated and passed down for generation after generation. If your maps get corrupted, or the knowledge of how to read them is lost, You can literally fly past your target without knowing it. What started as a precise trajectory can, with small errors over long times, turn into a miss by trillions of kilometers. So now, put all of that together. You're asking human culture to hold a single clear objective, reach Kepler-22b and settle it, through thousands of years of language drift, value shifts, informational decay, and changing external data about both the ship and the destination. There is no backup, no resupply, no direct control from Earth. The realistic outcome is that the project stops being our mission after a few generations and becomes their world with its own priorities. And even if, against the odds, they keep the goal, hold the course, and arrive in the right star system, another question hits hard. If the journey twists your civilization this much, and if you never had detailed, high-resolution data about the planet to begin with, what exactly are you arriving at? And what hidden threats are waiting there that you could never have planned for from 600 light-years away? How sane is it to burn a civilization's worth of energy going to a planet when right now you do not even know if it has a solid surface you can stand on? That is the situation with Kepler-22b. You can list some basic numbers, but the things that really matter for humans, pressure, chemistry, geology, weather, are still unknowns, and some of the likely options are flat out hostile. Here is what you actually know. You have a radius around 2 to 2.4 timed Earths. You have an orbital period, roughly 290 Earth days. You have a rough mass estimate on the order of several to maybe a few dozen Earth masses, with a best guess around 9 Earth masses. From that you can say super Earth in the habitable zone. But you do not know the surface pressure. You do not know the detailed atmospheric mix. You do not know how thick that atmosphere is, or where the clouds sit, or whether there is a hard rocky surface at all, up where the pressure and temperature are manageable. That means, in practical terms, the planet's basic geography is guesswork. It might have continents and shallow seas, it might be covered in a deep global ocean, it might be wrapped in a massive gas envelope where the transition from gas to liquid to solid is deep down under insane pressure. You are talking about dedicating thousands of years of ship time and a ridiculous energy budget to reach a target whose key features are still maybe this, maybe that. Take the case that sounds friendly at first, the ocean world. Suppose Kepler-22b is covered by a global ocean, hundreds of kilometers deep with no continents poking above the water. At 2+ Earth radii and something like 2 to 3 g surface gravity, the water at depth is under pressures far beyond what Earth's deep oceans produce. The deeper you go, the faster pressure rises, because gravity itself is stronger. That turns deep-sea engineering from hard but possible into you are well outside known material limits. If you try to build floating habitats, you have to anchor them, supply them and protect them from storms in an atmosphere that you still barely understand. If you want seafloor bases, you're placing them under unknown pressures, with unknown chemistry, possibly in layers where water is in exotic states, not liquid the way you know it, but hot, dense, and aggressive toward equipment. And remember, everything you build there starts its life inside a ship that has to carry all the material and industrial capability across 600 light-years first. Now look up instead of down at the atmosphere itself. You know that Kepler-22b sits in the habitable zone, so in theory an atmosphere of the right thickness and composition could support liquid water somewhere. But that does not tell you what the composition actually is. It could be carbon dioxide rich, like Venus, where a runaway greenhouse drives surface temperatures high enough to melt lead, even though the planet is not that far from Earth in terms of distance from the Sun. It could be methane heavy, like Titan, with hydrocarbon hazes and lakes of liquid methane or ethane. It could be hydrogen dominated like a mini Neptune, with a thick, light atmosphere that stretches high above deeper layers. Each of those regimes is a different kind of problem. Carbon dioxide-rich atmospheres can be corrosive and crushing. Methane-loaded atmospheres can give you flammable or explosive mixes if you introduce oxygen. Hydrogen-dominated atmospheres are very light but can be deep and stormy, and may interact badly with metals and electronics. Some of these chemistries can eat away at your structures, poison humans outright, or turn simple leaks or spills into explosions. You cannot assume that you can just walk out with an oxygen tank and a suit and treat the place like a rough Earth. Then ask the question people like to jump to, what if there is life there? On one hand, that would be a huge scientific win, proof of a second origin of life in the universe. On the other hand, you do not want to share an ecosystem with it. On Earth, your immune system is tuned by millions of years of co-evolution with local microbes. Even then, diseases like smallpox, plague, and various viruses have killed huge numbers of people. That is with pathogens that rely on the same basic biochemistry you do: DNA, proteins, familiar cell structures. On Kepler-22b, if life exists, it might not use DNA at all. It might run on different polymers, different amino acids, different cell chemistry. You cannot assume that it's harmless, or that it's easy to disinfect. It might not even recognize you as food in any familiar way, but it could still damage you chemically, trigger unknown reactions, or wreck your own microbiome. Even simple environmental exposure, breathing trace compounds, touching local water, could cause long-term problems because your biology has never seen anything like it. And that is just from the point of view of health. There is also the question of ethics. Landing humans, with their own bacteria, viruses, and engineered organisms, on a world that might host its own fragile biosphere, is the ultimate contamination event. You do not just risk killing yourselves, you risk wiping out a whole alien ecology before you even understand it. From 600 light years away, you cannot judge that risk honestly. You can only guess. The really bitter scenario is this: Kepler-22b turns out to be almost habitable. Not obviously dead like Mercury, not obviously hellish like Venus, but just off in ways that matter. Maybe it has too much greenhouse effect, so surface temperatures are just a bit too high for human comfort and long-term agriculture. Maybe it lacks a strong magnetic field, so its radiation environment at ground level is harsh. Maybe the surface gravity sits in that 2 to 3G band where human bones, joints and hearts simply cannot function for long, even with the best medicine. In that case, you arrive after 10,000 years of voyage, after a slow grinding filter of radiation, engineering and social pressure, and you find a world that is close enough to tease you but not close enough to accept you. The clouds look right from orbit, the spectra show water, maybe even oxygen or other interesting gases, but the combined package, gravity, pressure, chemistry, radiation, adds up to not for you. You can orbit, you can drop probes, you can build small sheltered outposts if you pour in enough technology, but you cannot just walk out and build a normal open sky civilization. So now the question shifts again. If the journey is this hard and the destination is this uncertain, with a real chance of being almost but not quite usable, does it make any sense to risk a civilization-scale mission when you could use the same resources to massively upgrade life back in the solar system instead? How many times would you have to pay for the International Space Station before you even scratch the surface of a real Kepler-22b mission? 10 times, 100, 1,000. When you stop thinking in rockets and start thinking in budgets, the picture gets even worse. This is not too expensive for NASA. This is too expensive for a planet that still has bills to pay at home. Start with real numbers you can understand. The International Space Station, built over decades, involved multiple countries and cost on the order of $100 billion. Big flagship programs like Artemis, which aims to return humans to the moon, or a serious crewed Mars program, live in the tens to low hundreds of billions range over time. Those are already huge financial lifts. They require alliances, long-term planning, and constant justification. Now compare that to an interstellar arc aimed at Kepler-22b. You're talking about building a rotating habitat the size of a small city, or many such habitats linked together. You need shielding that could be meters thick, engines pushing toward a significant fraction of light speed, gigantic power systems, complete life support and industrial ecology, and a launch infrastructure that can assemble all of that in space. The cost is not just more than the ISS, it is many orders of magnitude more. Realistically, you are in a regime where the project could absorb a significant fraction of global GDP for generations. That is where opportunity cost hits. Every terawatt of power you feed into beamed propulsion, fusion reactors, or antimatter factories is a terawatt you do not use for anything else. That power could run cities, replace fossil fuels, desalinate water, drive heavy industry, or support data centers and research labs back on Earth. Diverting that into an interstellar launch means asking billions of people to accept fewer improvements in their own lives and slower progress on urgent problems like climate mitigation and health in exchange for a mission whose payoff is thousands of years away. And what is the payoff exactly in any meaningful human time frame? Earth orbit satellites pay back quickly. They give you global communications, weather forecasting, GPS navigation, imaging for agriculture, disaster response and security. Robotic missions to the Moon and Mars deliver science, engineering practice and national prestige. Even a serious Mars colony attempt, though risky, would generate tangible results within decades. New technologies, resource extraction, planetary science, and the start of a backup for human civilization. Now put that next to a Kepler-22b arc. You spend centuries building the infrastructure, centuries feeding power into it. Then you launch a ship that disappears into the dark out of direct contact, and if everything works perfectly, a distant branch of your descendants might arrive and send a signal 12,000 years later. There is no near-term return on investment. No new data in your lifetime, no usable tech spin-off that you could not also get from much closer, much easier projects. Economically, it is a black hole. Then think about risk concentration. If you pile a huge slice of your industrial capacity into one or a few massive starships, what happens if one of them fails? A launch accident, a structural flaw in the design that only shows up after a few decades, an unexpected piece of physics. Any one of these could wipe out centuries of investment in one blow. Smart risk management says, diversify. Spread your efforts across many smaller projects with shorter feedback loops. Betting everything on Kepler-22b is the exact opposite of that. And there are obvious, easier wins much closer to home. With the same industrial power and budget that you would pour into a single interstellar arc, you could terraform at least parts of Mars over time, thickening its atmosphere, warming its surface, and building vast underground and surface habitats. You could construct O'Neill cylinders, giant rotating space colonies placed in safe orbits in the inner solar system, each one capable of holding hundreds of thousands or even millions of people in controlled environments at 1G. Go even further and you can start building large numbers of orbital habitats and solar power collectors around the Sun, not a full Dyson sphere, but a growing swarm of structures that tap a small fraction of the Sun's output. That alone could support trillions of human or post-human beings in comfort, with rapid communication and trade, near-instant rescue possibilities, and short travel times measured in hours, days, or weeks instead of millennia. The engineering is still hard, but compared to a 600 light-year mission, it is a factor of 10 or 100 easier in almost every dimension. From a rational planning point of view, you would always do these closer, scalable projects first. They give you experience with life support, radiation shielding, large-scale construction in space, and long-term governance, all within a region where you can still send help, still send spare parts, still intervene if something goes wrong. They also give you options. If you discover that long-term closed habitats have failure modes you cannot easily fix, you can adapt without having a billion people locked into a dead-end starship. So the economic verdict is cold and simple. A Kepler-22b arc is not just expensive, it is beyond any realistic budget for a civilization that still needs to survive on its home world. It demands energy and money on a scale that would delay or damage everything else humanity could do with that same effort. It gives almost no short or medium-term return, and it concentrates risk into a few gigantic fragile assets. In a universe where closer, safer, more flexible options exist, that is a bad trade. And even if you ignore that, Imagine you somehow push through, build the ship, pay the cost, accept the risk, and launch anyway. You still have to point this thing, keep it on course, and talk to it across centuries and then millennia, with no GPS, no real-time control, and a destination that you have never seen in detail. How do you navigate and communicate when every correction arrives hundreds of years too late? How do you aim at a planet 600 light-years away and actually hit it, when even tiny mistakes turn into misses bigger than whole star systems? Once you push a ship to a serious fraction of light speed, navigation stops being a background job and becomes another wall you have to break through. And this one does not care how good your engines are. First problem, the trajectory. To hit a target like Kepler-22b 600 light-years out, your initial path has to be insanely precise. A tiny angle error at the start, a fraction of a degree, grows and grows over trillions of kilometers. By the time you cross interstellar distances, that small misalignment can translate into you passing millions or billions of kilometers away from where you wanted to be. You're threading a needle from one end of the galaxy to another, and any small push you did not account for, any tiny miscalculation, shows up as a huge offset at the far end. And space is not perfectly smooth. On the way, your ship will feel gravitational tugs from passing stars, from dense clouds of gas and dust, from unseen objects like brown dwarfs or compact remnants. Each of those tugs might be tiny, but over thousands of years, all those little pulls add up. A course that was perfect in your launch simulation slowly drifts. If you do not constantly update your model of the galaxy around you and correct your path, those deviations can take you off target by a long way. Now remember, you do not have GPS out there. There is no network of satellites broadcasting your position. You navigate by looking outward at background stars, pulsars, and quasars. Pulsars, rapidly spinning neutron stars, can act like precise cosmic lighthouses, each with a unique pulse pattern, so by timing their signals you can figure out where you are. Background galaxies and quasars give you fixed points far beyond the Milky Way, stable over long periods. This works, but it is slow and noisy. You have to collect data, average signals, compare against models, and that all takes time. At relativistic speeds, where you are covering huge distances every second, small errors and delays in your position estimate matter a lot. Even if your pulsar navigation gives you good precision, any tiny model error, any wrong assumption about how a particular pulsar is drifting or glitching gets multiplied over centuries. The result is the same story, small mistakes now, big misses later. Communication makes it even worse. At 600 light-years, a radio message from Earth takes 600 years to reach the ship, and a reply takes another 600 years to come back. There is no such thing as live troubleshooting. If something strange shows up on your sensors, you cannot send a screenshot to mission control and wait for an answer. By the time any advice arrives, the crew that asked the question is long dead, and the ship is centuries further downrange. That means every serious decision, navigation corrections, engine management dealing with unknown objects ahead, all of it has to be handled locally by the ship's own people and their descendants. Earth can send general guidance, long-term science, maybe updated maps of the galaxy, but it cannot run the mission in real time. Once you are a few light years out, you are basically a sovereign civilization with a very slow mailbox. Now, think about the tools you use to navigate hardware and software. Today's spacecraft already struggle with obsolescence. They fly with computer chips that are old by consumer standards because space-qualified electronics have to be robust and heavily tested. Software updates are careful, infrequent, and risky. Even then, we run into bugs, memory limits, and radiation-induced errors over just a few decades. An interstellar ship does not get to reboot its tech every 5 years. It must carry not just one navigation system, but the ability to maintain, emulate, or completely rewrite its own navigation systems across centuries. You have to assume that computing paradigms will change multiple times. Maybe you start with classical silicon hardware, then move to quantum processors, then to something biological or neuromorphic. Through all of that, the core navigation math, the understanding of pulsars, of galactic dynamics, of relativistic corrections, has to remain consistent and testable, or you slowly lose track of where you really are. That means you're not only preserving data, you're preserving how to interpret that data, how to code it into new systems, and how to trust the results. If you get that wrong, you can have a shiny new computer running a corrupted version of a centuries-old algorithm, making small mistakes that nobody notices until it is far too late to correct. Finally, after thousands of years of this, you start to arrive. You begin to slow down relative to the Kepler-22 system, and now you have a new problem. You're approaching a world you have never seen in high resolution. The Kepler Space Telescope detected Kepler-22b by seeing its star dim slightly when the planet transited in front of it. That gives you size, orbit, and some rough clues, but no surface map. Even next-generation telescopes like the James Webb class and beyond can give you spectra, maybe a hint of clouds, maybe very rough weather patterns, but not the kind of detailed charts you use for landing on Mars or the Moon. So you are decelerating a massive starship, or a fleet of them, into orbit around a planet whose real terrain, real storm systems, and real hazards you're only seeing clearly for the first time as you arrive. The people who designed your sensors and landing systems died thousands of years ago. Their design assumptions were based on distant observations and models that may now be outdated or incomplete. You have to trust that your descendants have maintained, updated, and cross-checked all that tech without ever having a chance to test it on anything truly similar. You can send scouts and probes ahead of the main ship, but even then, you are testing in real time, at the end of a journey where failure means you have nowhere else to go. There is no second nearby planet you can divert to in a few months. There is no fuel depot waiting. You either get orbit insertion and landing right, with hardware and procedures that have survived a multi-millennia relay race, or you lose everything. So after all of this, you might think, fine, let's dodge the hardest parts by simply skipping the living crew. Put people on ice, or put minds in computers, sleep through the hard centuries and wake up at a Kepler-22b like nothing happened. But the laws of physics and biology do not let you off that easily either. And when you look closely at cryonics, suspended animation, and extreme time dilation, you run into yet another wall. So at this point, you might try the classic escape move if the journey is too long and too harsh. Why not just freeze everyone, skip the boring part, and wake up at Kepler-22b like nothing happened? On the page, that kills the whole problem in one line. In real physics and real biology, it barely gets off the ground. Start with cryonics versus actual thermodynamics. When you freeze normal tissue with water in it, ice crystals form. They slice through cell membranes. They wreck internal structures. Modern cryonics talks about vitrification, turning the water inside cells into a kind of glass, not solid ice, by cooling fast and using special chemicals. That helps with short to medium-term storage, but it does not magically pause chemistry forever. Molecules still jiggle a little, materials still slowly change, and over long spans, you get damage. Right now, what we can do reliably is simple. We can freeze embryos and some very small samples for decades and bring them back. That is impressive, but an embryo is a tiny cluster of cells. Your brain is billions of neurons, each one wired with thousands of synapses. The thing you actually care about, your memories and personality, live in those detailed connection patterns. Freezing and reviving a full adult brain without losing that information is a completely different level. You do not just need the cells to survive, you need the exact wiring and strength of every link to stay intact. We do not know how to do that, we do not know how to verify it even if we tried, and we definitely do not know how to keep it perfect for thousands of years. People then point at suspended animation and say, fine, we will not freeze solid, we will just slow metabolism way down. There are animals that sort of do this. Tardigrades, some worms, some tiny creatures can dry out or freeze, enter a state called cryptobiosis, and then wake up years later. Human medicine can cool patients during surgery, drop body temperature for hours, and reduce damage during things like heart operations, All of that sounds like a path toward long sleep. But look at the numbers. Those animals do years in special conditions, and they are tiny. Human medical cooling works for hours, maybe a bit longer in special cases, not for decades. Nothing we have seen scales to centuries, let alone tens of thousands of years. Keeping a complex, warm-blooded mammal in a controlled, low state, without constant active support for that kind of time, is not just an engineering problem, it is a fundamental biological one. Cells need to repair themselves, proteins degrade, DNA gets damaged by the background radiation. In a real ship, with cosmic rays coming through the hull slow but constant, anything asleep for millennia is still being hit. You're not pausing time, you're just making metabolism too slow to fix the damage as it accumulates. So then the conversation jumps one more step. If freezing the body is too messy, skip the body. Upload the mind. Scan the brain in insane detail, map every connection, every weight, and transfer that pattern into hardware. Now the crew is just software. In that form, you do not need a 1,000-ton life support bubble. You can store millions of minds on a small hardened device, run them at whatever speed you like, or pause them cleanly for long stretches. You can beam them as data or carry them on microscale hardware on a small, well-shielded probe. That does solve a lot of the physical problems, but it silently changes the question. You're no longer transporting human biology to walk on Kepler-22b under a skimmy, you're propagating an information pattern. Whether that pattern counts as human is a philosophical argument, not a physics one. If a copy of you wakes up in a machine orbiting Kepler-22b, it might feel continuous, it might not. But what is actually standing on the planet, if anything, is a robot body or a synthetic form, not a flesh and blood human that's set off from Earth. You avoided some of the pain by changing what going there means. Another favourite idea is to rely on relativistic time dilation. Go fast enough and time on the ship slows down compared to Earth. That means the crew could maybe experience a shorter trip while thousands of years pass outside. This part is real physics, but the way it gets used in casual talk is misleading. To get serious time dilation, you need speeds extremely close to light speed. Physicists describe this with a factor called gamma. When gamma is close to 1, time dilation is tiny. To get gamma values large enough to cut thousands of external years down into a human lifetime on board, you're talking about speeds like 90%, 99%, 99.9% of light speed. At those speeds, the energy cost explodes. The kinetic energy of each kilogram of ship mass is not just a little higher, it becomes many times the energy you would need at low speed. By the time you're at 99% of light speed, each kilogram of the ship costs roughly 7 times more energy in kinetic form than at non-relativistic speeds, and pushing closer to the speed of light makes that factor climb even more. For a ship of thousands or millions of tons, that is so much energy that you are beyond hard to imagine you're into completely unrealistic given any normal power source. You would need power outputs that make current global energy use look like a rounding error. And even if you could somehow deliver that energy and keep the ship intact under the resulting conditions, the environment becomes brutal. The interstellar medium at those speeds hits you with energies that make our earlier dust and radiation problems look small. Time dilation helps your subjective clock, yes, but it ramps up every other danger at the same time. Warp drives and wormholes are the final escape hatch people like to pull. The math of general relativity allows solutions like the Alcubierre warp metric, which bends spacetime so a bubble can move faster than light relative to distant observers, or traversable wormholes connecting two distant regions. But there is a huge catch. To build those solutions, you need exotic matter with negative energy density, something that behaves in ways no normal material does. We have never seen such matter in the lab. We do not know if it exists in usable form, and even if tiny quantum effects hint at something similar, scaling that up to starship size is pure speculation. So the universe, as far as our tested physics goes, gives you no real shortcut. You cannot outrun the light that left Earth after you. You cannot hide from the energy cost of going faster. You cannot pause chemistry and radiation damage for tens of thousands of years just by cooling things down a bit. Every realistic path either abandons the idea of sending human bodies as you know them, or abandons the idea of doing it on human timescales, or both, which leaves one more uncomfortable layer, even if you say, fine, we accept millennia, we accept post-human crews, we accept absurd energy use. The universe itself is changing slowly around you. Stars evolve, space weather shifts, and on the way to Kepler-22b, you're exposed to long-term cosmic hazards that stack on top of everything else you're already fighting. Here's another thing you cannot control. While you crawl toward Kepler-22b, the universe keeps moving and changing around you, including the very star you're heading for. You're not aiming at a frozen picture. You're aiming at a system that is evolving on its own clock, under its own physics, with zero obligation to stay friendly until you arrive. Kepler-22, the star, looks comfortable on paper. It is a G-type star, similar to the Sun but a bit less massive and a bit less luminous, with an age of roughly 4 billion years. That sounds good, right? Not a violent baby star, not an exhausted red giant, something broadly in the same life phase as the Sun. At first glance, that feels like a green light, a stable heater for a long time. But stars do not sit still. Over billions of years, their luminosity slowly goes up, their habitable zones creep outward, and planetary climates shift. Earth itself is not permanently safe. Long before the Sun actually swells into a red giant, its increased output will likely make Earth's surface uninhabitable, pushing us toward runaway greenhouse conditions. Now, your trip to Kepler-22b is only on the order of thousands to tens of thousands of years, so you are not directly hit by the billion-year trend, but that does not mean you are safe from shorter-term stellar variability. Even Sun-like stars have active cycles. Our own Sun runs through an approximately 11-year magnetic cycle, with quiet periods and active periods. During active times, you see more sunspots, more flares, more coronal mass ejections, stronger solar wind. Parker Solar Probe, which dives in close to the Sun, has already shown how dynamic and structured the solar corona and the so-called Alfvén surface really are. The outflow of charged particles and magnetic fields is not smooth, it is full of switches, bursts, and complex structures. Now translate that to Kepler-22. You do not know its full activity profile. If it happens to have a stronger or more chaotic flare cycle than the Sun, its habitable zone can be a rough place. Repeated strong flares and coronal mass ejections can erode planetary atmospheres, especially if the planet's magnetic field is weak or its upper atmosphere is easily stripped. They can hammer any magnetosphere, raise radiation levels at the top of the atmosphere, and disturb climate patterns. Between the time you launch and the time you arrive, tens of thousands of years later, those cycles could significantly change the surface conditions, even if the average brightness of the star is only nudged up a little. And the star is only part of the story. Your ship is not travelling through a clean vacuum, it is moving through the galaxy. As you orbit the Milky Way, you pass through regions with different densities of gas, dust, and cosmic rays. Some stretches are relatively calm, others are near the remnants of old supernova explosions or near denser molecular clouds. Passing through those harsher zones can spike your radiation exposure, increase the flux of fast particles, and raise the number of dangerous dust grains and small rocks in your path. The longer the trip, the more of these galactic hazards you integrate over. A short hop to Mars exposes you to a limited slice of the Sun's behaviour and the local environment. A 10,000-year run to Kepler-22b exposes you to a long chain of different environments, some of which you cannot predict well in advance. A single nearby supernova in the right place and time along your route could shower your ship with extra cosmic rays or change the density of the medium you're flying through. You do not get to roll those dice only once, you keep rolling for millennia. Put this together with everything else you're already trying to keep under control. You need Kepler-22's star to stay within a nice activity band, not too flare-happy. You need the planet's atmosphere and magnetic field, if it has one, to survive those flares and winds. You need the interstellar medium along your specific route to stay within the density range your shielding is designed for. You need your ship's own structure, engines, and radiation defenses to survive constant stress without a major, unfixable failure. You need the onboard civilization to keep its knowledge chain intact, so it can respond when sensors say, "Conditions ahead just changed." None of those things have to go wrong quickly. That is the trap. A single year looks fine, a single century might look manageable, but over thousands to tens of thousands of years, the probability that something nasty happens somewhere in that chain climbs and keeps climbing. You are betting against a universe that statistically prefers failure over long enough timescales. Materials fatigue, electronics glitch, people make mistakes, stars burp, space throws debris, and radiation slowly eats away at everything. So the plan in its full form demands that the star stays friendly, the planet stays stable, the interstellar environment along the way does not hit you with a rare but deadly event. The ship stays structurally sound, and the onboard society stays technically capable and motivated, all at the same time, for a time span longer than all of recorded human history. That is the stack of conditions you are laying on top of the already brutal requirements of propulsion, life support, and shielding. And here is the final twist this sets up. Even if you somehow satisfy all of that, even if everything goes mostly right, the universe is big enough and the exoplanet catalogue is growing fast enough that by the time you are actually capable of building an interstellar ark, you will probably know about dozens of better, closer, safer targets than Kepler-22b. The mission you started to chase a first habitable world might look, from the future, like a huge overcommitment to an outdated goal, which raises the next hard question. If there are closer habitable zone planets, and if you can build vast habitats and megastructures right here in the solar system, why would any sane civilization still choose to spend everything on a 600 light-year throw toward a world that was only exciting because it was discovered early? How smart is it to lock into Kepler-22b when, by the time you could actually launch, it will probably be just one entry in a huge list of nice but not special planets? The cruel part is, Kepler-22b mattered mostly because it was early. Our technology for finding exoplanets exploded, and it kept going. Since Kepler-22b was announced in 2011, we have confirmed thousands of exoplanets. We now see small rocky worlds, super-Earths, mini-Neptunes, hot Jupiters, you name it, around all kinds of stars. We have found planets in habitable zones much closer than 600 light-years, and the catalogue is still growing. Statistically, with hundreds of billions of stars in the Milky Way, it is almost guaranteed that there are planets in habitable zones tens of light-years away, not hundreds. From a pure probability standpoint, Kepler-22b is not the one, it is just a data point that showed us such worlds exist. Now overlay that with time. Say you decide somehow to start building a 10,000-year mission to Kepler-22b. You pour industrial power into it, you build the ark, you aim, you launch. Meanwhile, back in the solar system, telescopes keep improving. A century after launch, you have new observatories, interferometer arrays in space, maybe telescopes parked far from Earth in stable orbits. Those instruments start to resolve atmospheres of nearby planets in detail. Then you find it, a rocky planet in the habitable zone, 20 light-years away with better gravity, better chemistry, better everything. At that moment, your Kepler-22b mission becomes a cautionary tale. Your ship is locked on course to a more distant, less optimal target, with older technology and no easy way to recall or redirect it. The civilization that launched it is now looking at a closer, superior option, and all they can do is watch power and resources already spent drift away. You turned what was meant to be a bold first step into a long, expensive commitment to yesterday's map. Compare that with what you can do locally using the same energy budget. The power required to accelerate a multi-million-ton ship to 10 or 20% of light speed is ridiculous. If you take that power and use it instead to build infrastructure in the inner solar system, you can do things like Dyson Swarm-style solar collectors huge sheets or swarms of satellites that capture sunlight and beam energy where you need it. You can build large numbers of O'Neill cylinders, rotating habitats that provide comfortable 1G environments, Earth-like lighting, and controlled climate, all orbiting safely where help from home is hours or days away, not millennia. Each of those cylinders could host hundreds of thousands or millions of people. A swarm of them, plus industrial platforms around Mercury, Mars, and in the asteroid belt, could multiply the living area available to humans by orders of magnitude. That is effectively unlimited expansion, without ever crossing more than a few light minutes from the Sun. You get scalable growth, short feedback loops, and the option to course correct your civilization as you learn. Science-wise, the argument for going physically to Kepler-22b gets weaker every year. JWST class telescopes and the ones that will follow can already read exoplanet atmospheres by looking at how starlight filters through them during transits. From here in the solar system, we can detect water vapor, carbon dioxide, methane and other gases. With bigger baselines and interferometry, future instruments could map rough cloud patterns, measure temperature gradients, and even search for biosignatures like unusual mixes of oxygen and methane that hint at life. None of that requires a starship. You do not need to sit on Kepler-22b's surface to know it has clouds or oceans or a greenhouse problem. You can do that with photons, not rockets. The cost is high, but it is tiny compared to building and launching a world ship, and the results come back in years and decades, not thousands of years. You also get data on many planets, not just one. That means you can compare, choose better targets, and refine your models. So ask a blunt question. In what kind of future does it make sense to still send biological humans on a 600 light-year one-way trip? By the time your civilization is advanced enough to even consider a serious Kepler-22b arc, it will likely already have huge orbital habitats, mature asteroid mining, automated factories in space, AI probes that can travel faster and cheaper than any human ship, and telescopes that can dissect faraway atmospheres with fine detail. In that context, putting fragile 80-year lifespan bodies into a metal shell and flinging them into deep time starts to look less like brave exploration and more like reckless waste. And remember, every year your local system infrastructure improves, the relative value of sending physical humans drops. Why risk multi-thousand-year biological missions when you can send swarms of small AI probes, or later digital mines, at far lower cost and risk? Why hard commit to a single distant world when you can float above many worlds virtually and pick your moves with actual data? So by the time you're technologically capable of even dreaming of a real Kepler-22b voyage, you probably will not want to waste the resources on it. You will have better targets, better tools, and better ways to explore. The romantic idea of let's go live there will have been replaced by something colder but more realistic. This is not the way humans reach the stars. Which brings you to the final verdict. When you stack up distance, propulsion, the interstellar environment, time, biology, economics, and changing knowledge, you see that Kepler-22b is not a destination for humans at all. It is a mirage that keeps dissolving every time you try to walk toward it. The real question is not how do we get there, it is what does that tell us about what our future among the stars actually has to look like? Here's where all of this really lands. You are not up against one big problem with Kepler-22b, you are up against 4 hard walls at the same time: distance, propulsion, environment, and timescale. Each one on its own is brutal. Put them together, and for baseline humans, they are effectively a stop sign. Start with distance again. 600 to 640 light years, trillions of kilometers, trillions of miles. Even at 10% of light speed, you're looking at around 6,000 years of travel. That is longer than all of recorded history. Propulsion says, to even get close to that speed with a ship big enough to hold people, shields, food, water and industry, you need energy on the level of tens of thousands of times current annual global power use just to speed up and slow down one vehicle. Environment says, in deep space at those speeds, dust grains hit like bullets, cosmic rays tear through DNA, and you need meters of shielding that turn your ship into a small world. timescale says your life support, your industry, your training, your culture all have to keep working, not for 50 years, but for 10,000 years, with no outside help. You're trying to cross light centuries with chemistry-based apes who live maybe 80 years, whose systems flip every few generations, and whose institutions rarely stay stable beyond a few hundred years without major changes. That is not an insult. That is just what humans are like. You're taking a species built for short, fast feedback loops and dropping it into a project that does not fully pay off for hundreds of generations. Now, physics does not forbid going to the stars in general. That is important. The laws of relativity do not say no travel. They say no shortcuts faster than light, no cheating on energy. In principle, there are things that could cross 600 light-years and still care about the result. Self-replicating robotic probes could hop from star to star, using local resources, repairing themselves, splitting into copies, exploring slowly but persistently. Uploaded minds, if you ever build that tech, could live as software on hardened hardware, hopping on small probes that do not need air or food, that sleep for centuries and wake up only when needed. Fully post-biological entities, whether AI or something built from humans, could treat 10,000 years as just another long project. But notice what those ideas all have in common. They are not sending unmodified human bodies to go live on a distant planet the way we live on Earth. The popular picture, launch a crew, cruise for a couple of years at sci-fi speeds, and step out on Kepler-22b's beaches is not just unlikely, it is flatly incompatible with everything we know about relativity, energy budgets, radiation, life support, and human social behaviour. There is no way to compress 600 light-years into a there and back in one lifetime trip without breaking physics. That does not make Kepler-22b meaningless. It actually gives the planet a different, more realistic role in our story. When it was announced, it proved something important. Sun-like stars can host planets in the habitable zone, and they are not rare weirdos. It helped push the field from do such worlds even exist to how many of them are out there. There's a data point that says the galaxy is probably full of planets where temperatures, at least somewhere in the atmosphere, could allow liquid water. So Kepler-22b is not our next home. It is one of the first clear signs that potential homes exist at all. It sits there as a marker, telling you, keep looking, there are more, that is a huge scientific win, but it is a very different thing from being a practical destination. Meanwhile, there is a lot you actually can do that does not fight every wall at once. You can build a civilization that fills the solar system. That means turning Mars, the Moon, and the larger asteroids into industrial and scientific hubs. It means building O'Neill cylinders in orbit, rotating habitats that give you 1G gravity, Earth-like conditions, and controlled climates above worlds that are otherwise harsh. It means using metric as your working language because you're building real machines, but keeping miles and feet around when you need to talk to normal people about how big and how fast things are. You can send fleets of small, fast probes to nearby stars like Alpha Centauri 4.3 light-years away instead of 600. With advanced laser sails, you could push gram-scale probes to 20% of light speed and get there in a couple of decades of travel, not thousands of years. Those probes can take close-up images, do detailed spectroscopy, and beam the data home. That is still hard, but it is within view of the kind of tech trajectory we're already on. You can also keep watching Kepler-22b itself from a distance. Future telescopes, much bigger than what we have now, can measure its atmosphere, if it has one, read its greenhouse gases, look for clouds, maybe even spot large-scale patterns that hint at oceans or strong weather systems. You can learn what kinds of planets nature builds at that size and orbit, how common mini-Neptunes are versus true rocky super-Earths, and how often habitable zone really lines up with actually habitable. All of those paths give you real knowledge, real growth, and real security, without demanding that you risk nearly everything on one long silent throw toward a world you hardly know. So here is the shattering realization that sits under this whole story. When you run the numbers precisely, Kepler-22b is not a destination for humans. not in the form you recognise as human today. It is a beautiful mirage, a world that lights up your imagination when you hear Earth-like and habitable zone, but that falls apart as a practical goal once you include distance, engines, radiation, life support, culture and time. What it really shows you is that the universe is bigger, harsher, and older than our travel dreams. Light years are not just big numbers, they are deep cuts into everything that makes human life feel normal. And the quiet twist is this: the future of us among the stars probably does not look like bodies in rockets, planting flags on faraway beaches. It probably looks like something more alien, more distributed, more digital or engineered, something that a person from today might struggle to even call human at first. Kepler-22b sits out there as a reminder of that gap, a shining maybe, that forces you to confront what it would actually take to cross 600 light years, and who or what would really arrive at the other end. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.